we have decomposed the problem of analyzing workflows into understanding the events, people, decisions, and consequences involved, and how they are observed and authorized. And we've looked at how this creates a core loop for people to make business decisions. Now we'll turn our attention towards the need for testing, how to think about scaling, and managing the situations where contention between workflows can occur. So far, we've used an example application, a digital trading card market, to explore how we might create a workflow appropriate for a distributed ledger application. As we've analyzed this simple workflow, we've come up with a simple action-oriented design. After some adaptation to accommodate the pragmatic concerns associated with production, this sort of simple design will work for the vast majority of workflows in a Daml application. The places where this approach won't be sufficient are the workflows that drive the scaling and performance ceiling in your application requirements. Using either a data-oriented design or this sort of simple action-oriented design for these requirements-defining workflows will at best result in a need to over-provision hardware. And, at worst, can result in levels of contention that can make meeting the requirements impossible. First, some general advice. Nothing beats testing, so start testing for scale early and often. Unlike software optimization, this sort of information schema optimization is something that needs to be done early in the development process. The Daml models developed at the beginning of the project become the foundations that structure a lot of downstream code and application development. As in most things, changing foundations can be difficult and invasive, so leaving scaling and performance considerations to the end of a project can result in significant rework. So it is important to include testing of key performance and scalability benchmarks as early as is feasible, and to keep testing throughout the development process. You can get a lot of Daml application scalability from vertical and horizontal scaling of the participant and domain nodes. With a suitable Daml model, you can truly provide incredible performance and scalability by a combination of vertical and horizontal scaling of participant and domain nodes. Critical to efficient scaling is ensuring your model supports full utilization of the resources deployed to support it. The primary cause of underutilization is workflow contention. In the worst case, excessive contention between workflows can prevent any ability to scale the application. Contention occurs when multiple workflows attempt to exercise consuming choices on the same contract. This issue is almost inevitable if you have used data-centric modeling techniques, especially the relational database schema design techniques we are all used to. A common example of this is when a model is denormalized, resulting in a centralized holding contract. Every transfer in and every transfer out of the holding now has to queue to adjust the balance on this single contract, as if we had a supermarket with only a single cash register that can only process one item at a time. In a supermarket, the solution is simple. Allow multiple items to be sold in a single transaction and allow multiple cash registers to operate simultaneously. And with most Daml models, for example, the problematic holding contract, the solution is analogous. Allow multiple transfers to be applied to the holding in a single transaction, and allow the holding to be split over multiple contracts that can be updated simultaneously. Now we will look at these in more detail. But first, to reiterate, if you take nothing else away from this lesson, let it be these three things. Test for scale early and often. Allow vertical and horizontal scaling by managing contention. With consistent attention to these three things, the vast majority of performance and scalability issues will be avoided. To try to gain an intuition for Daml optimization, let's consider again the point-of-sale example. We are setting up a store that will sell things and settle transactions for money. We have workflows that involve staff providing advisory services that ultimately result in a sale that will use a cash register. The advisory services may be very complicated and take several minutes to complete, but ultimately every advisory workflow will need to use a cash register to process the transaction. When we design for a workflow, it is common to simplify things. In this example, we'll have one customer, one advisor, one sale, and our design will end up with one cash register. We may well implement a small proof of concept along these lines and prove that one cash register is sufficient for a small store with only one staff member serving one customer at a time. This is where a failure to test the real performance and scalability requirements can bite. As long as we only need to support one staff member and 2 or 3 concurrent customers, this model will prove incredibly simple and flexible. In fact, at that scale, it is an ideal solution to the problem. As we increase the number of customers, though, we will find we have to increase the number of staff. If we don't, then the high latency of the long-running advisory services will dominate and our throughput will be limited. If the advisory services take 5 minutes, then a single staff member sets a hard upper limit of 12 transactions per hour, and it doesn't take a lot of customers to see latencies climb to half an hour or more. Now we have to revisit our design because we have multiple staff. We are going to need to consider how our workflow allocates a customer to a staff member and ensure the staff processes have the resources they need to operate independently. Still, even with 3 to 4 staff members, we can probably get by with only one cash register if we allow a short but manageable queue. Of course, we may need to revisit our simple design again and include this queue, or else a disorderly rush for the register may cause problems. Eventually, as we increase the number of customers and staff to match, the queue stops being a transient, occasional thing and becomes a permanent part of the workflow that every transaction has to navigate. And still, it might be manageable for a while if our latency requirements are flexible enough. If our scaling requirements demand we service customers beyond this point, then adding more staff will not help. At some point, the contention for the cash register comes to dominate the entire workflow experience. If it takes 30 seconds to process a transaction through the register, that sets a hard limit of 120 transactions per hour. But the system will be unworkable long before we reach that limit. Instead of per hour, let's assume that we want to handle 120 transactions per minute. How might we achieve this? This is where the 2 approaches we mentioned at the outset come in. Allow multiple items to be sold in a single transaction and allow multiple cash registers to operate simultaneously. The first approach finds its use in almost every performance remediation, as it generally has the smallest impact on the existing system. This might seem counterintuitive, because adding more cash registers probably doesn't affect the sales workflow much. But recall what we said earlier. Daml models form the foundations of a Daml application, and foundational changes late in a project can be expensive. The assumption of a single register quickly becomes embedded in other workflows, like end-of-day closeout procedures or real-time balance reporting. Once this assumption is there, changing it may require substantial changes to these other workflows. In a physical store, we might dedicate a staff member to collecting a batch of sales and processing them in a single transaction at the cash register. If we want to handle 120 transactions per minute, we will need to be able to process at least 60 transactions per batch. While this approach avoids changing the other dependent workflows, it does affect the sales workflow. We need to revisit our simple design as staff no longer access the register directly. Instead, they add their request to the batch and wait for it to be processed. Alternatively, we can use the second approach, installing multiple independent cash registers. Most of the time, this will produce a more flexible and scalable design. A Daml application is inherently a distributed application, and reducing the number of centralized points of contention is necessary to leverage Daml to its full potential. The impact of this decentralization on workflows that haven't been written yet is often minor, which is why this is something that becomes both more difficult and more expensive the longer you leave it. It is important to be considering your true scalability requirements as early as possible. Then start testing to find this point of contention now rather than in 6 or 12 months, after a dozen other workflows have been implemented assuming access to this single centralized contract. So if we can run 60 cash registers in parallel, we can meet the 120 transactions per minute throughput. Of course, we can do both batching and distributed concurrency, and our throughput limit would now be 120 transactions per second. A number in excess of requirements for our physical store, but a very reasonable expectation for a Daml workflow that has been designed to scale. Remember, the vast majority of workflows in your application will not need this treatment. Therefore, we don't want to add this complexity to every workflow. How do we identify where we need to apply these principles? Start by estimating the business transaction performance requirements. How many holding transfers? How many inventory acknowledgements? And how many sale completions? For each business transaction, identify which contracts/templates can be consumed by the relevant step in the relevant workflow. Then consider possible contention sources. What happens when we run multiple instances of a workflow concurrently? Do they end up needing to update or consume the same shared contract? What happens when we run the transaction in parallel with other workflows? Again, do they end up with multiple updates to the same contract that would therefore need to be queued or serialized? And are there any consequences from one step that become inputs that another workflow will need to wait for? Note that all of these involve updating a contact, which in Daml always involves contention on an archive operation, so that makes a good guide. Identify the workflows and workflow steps that want to archive the same contract. Then compare your numbers against a critical rule of thumb. Your design should not require better than 1 second round-trip latency to the ledger. A round trip has to prepare, then submit a transaction to the Canton ledger. Then validate and confirm the transaction was correctly committed to a ledger. This will normally take less than 1 second. However, to depend on being able to sustain better than that when the system is under stress will add risk and instability to your application. Consequently, any business transaction you estimate to have a contended archive performance requirement greater than or even close to 1 per second should be prioritized for early performance in scalability testing. Keep in mind peak load can be 10 to 100 times higher than the average load over a full day or full week. When doing this analysis, there is no substitute for understanding your business process. Using these principles on the targeted workflows that you identify as key to your system's performance and scalability requirements, it is possible to run thousands of business transactions per second. But only if you decentralize the shared contracts in critical workflows so they admit concurrent transactions. And then maximize the throughput per Daml transaction using batching to take full advantage of that concurrency. Then, test the scalability of your designs early and often.